All right, let's get started. I think we have almost everyone and it's 5 minutes past. Cool, so let me just start with kind of a quick reintroduction and then we'll kind of go over the course overall before diving into today's lesson. And then throughout the course, if anyone has any questions, please feel free to just speak up. I'll also be asking for input from you all as we go through the problems together. So it's a little bit, hopefully more immersive, and just feel free to speak up. If it gets too unwieldy, like too many people are speaking up, then we can use sort of the hands tool or something like that in the meeting. But let's just start by feel free to interrupt if you have any questions. From the kickoff meeting last week, I'll just quickly reintroduce myself because I know there are a lot of people. My name is Wendy. I'm going to be teaching this group with Matthew, and I'm just doing the probability and counting and probability. We're going to meet up every Tuesday for this class, and we'll go through over the next 6 weeks a bunch of topics in counting, different ways of counting, different techniques, and then we'll do an introduction to probability. So to kick it off, I wrote like a really quick intro. So just starting with what is combinatorics. It's just a branch of mathematics that focuses on counting, and there's a lot of things that we can count. We can think about combinations and permutations of elements of sets, and we'll learn more about combinations and permutations later in the course. We can talk about arranging things, ordering things. We can also apply it to things like graphs and graph paths. So if some of you took the combinatorics pre-test, there was a question about paths in a graph. Also probabilities, and with probabilities we can count all the different possibilities and how many cases in the numerator and the denominator to calculate probabilities, and also more. And I want to highlight also, this is a pretty useful subject when it comes to contest math, but it's also an area of math that where there's a lot of active research and there's a lot of harder problems and open questions as well in this area, if you're interested in learning more kind of down the line. And then just really quickly, here's the list of topics that I hope that we can cover every week. Of course, we'll kind of adjust depending on how fast we get through things or how whether we run out of time or not. We meet every day from 3 to 5, same time as all the other classes. And then this week we'll start with just kind of an introduction to counting. We'll talk a bit about permutations and then some useful counting techniques, and we'll go with a lot of practice problems. Next week we'll talk a little bit more about combinations and kind of recap some of the techniques we learned this week. In week 3 we'll kind of go into some more advanced counting concepts. Week 4 we'll start probability and just do a quick introduction. Week 5 we'll kind of look into slightly more complicated topics like effective value and conditional, and then we kind of overflow review of all the things that we've covered, looking at probably some problems that use a bunch of these concepts as well. And then if you have any questions about this course, feel free to just pipe up. If you have any questions outside of class, use our Piazza group or off hours, which we will have on Friday. It's basically an open time for you to come and ask any questions you might have. All right, any questions on any of that before we jump into the content for this week?
The document that's on Piazza is different from this document.
Yes, the document in Piazza has more of the lecture notes, which we'll go through. And then this document just has kind of the overview. I'm happy to share it on Piazza afterwards as well.
Okay, okay.
Any other questions? All right. Cool. So we'll start with some counting. and start with just counting lists of numbers. And this is from the document that I shared on Piazza, and thanks to Matthew for providing the content. So we'll start with sort of a simple form of counting, which is just counting lists of numbers. And we can look at, for example, the sequence of positive integers, so like 1, 2, 3, 4, 5. This is often called the counting numbers. Other things you might hear are like natural numbers or whole numbers. They're all referring to the same set of numbers. And basically, we call a sequence of these sorts of numbers a simple list. So if we look at this list, I'm going to try highlighting this. This list, how many terms are there? Because this one's pretty self-explanatory. So there's 18 terms here. But using this concept, we can basically count some more complicated sequence of terms. So for example, maybe we have this list. We'll look at this one, 9, 13, 17, 21, 25, et cetera, to 909. So does anyone have any thoughts on how we could count how many numbers are in this list? And just feel free to chime in if you have any ideas.
I think that we could try to make it a simple list, do certain operations that every term in the list to bring it down to 1, 2, 3. Then the last term would be the amount of would be the amount of terms in the list.
Yeah,
How about
that's right.
using
Sorry, keep going.
No.
how about using the nth term?
Sorry, how about using the what?
Nth term.
Can you explain?
You can use algebra to calculate it.
Sorry, say that again.
Nth term.
The nth term?
Yes, please.
Yeah, so we want to see how many for n, sort of how many terms are there. And so if you think about like how we express these terms, we could basically think about how to make this into a simple list. And so one thing we notice here is that the difference between each of the numbers is constant, so it's always 4. So this is plus 4, plus 4, plus 4. And then we also notice that each of these is 1 more than a multiple of 4. So 9 is 1 more than 8, which is a multiple of 4. 13 is 1 more than 12, which is a multiple of 4. And so if we subtract 1 from every term, we get this sequence. So basically what we did was we took 9 minus 1 becomes 8, 13 minus 1 becomes 12, etc. And then we can divide by 4. What does that give us? 8 divided by 4 equals 2. 12 divided by 4 is 3. 16 by 4 is 4. And then 908 divided by 4 is 227. So now we have a much simpler list, right? We have 2, 3, 4, 5, 6, etc. to 227. And then if we want to make it in the form that we've had before, which was starting from 1, then we can subtract 1 from every list, or sorry, from every term in the list. And then that gives us 1, 2, 3, 4, 5, 6 to 226. So that is an easier way for us to kind of see, oh, there's actually 226 terms in the list. And therefore, there's 226 terms in this arithmetic sequence, this original one that we had. Does anyone have any questions about how we came to this answer or why we did it this way?
Yeah, I have a question.
Yeah.
why wouldn't it be like wait, no, I answered. I was gonna ask, wouldn't it be 227 terms if you're including all of it? But then I realized that doesn't make sense.
Oh, I see. I see. Yeah, we'll talk about a little bit later, just like general formulas for finding the number of terms here. But yeah, so here, since we're starting with 1 and going to 226, there's 226. Here it goes to 227, but it starts at 2. So that's why there's 226 terms.
I have a question, please.
Yeah.
So is there like a particular process for every single time you find the number of terms, or is it just like an example? Like, how do we figure out like what we should do to find the number of terms?
Yeah, so this is an example, and we'll go through a couple more examples before we generalize. So let me go through a couple more, and then we can talk about kind of formulas for some of these. In this case, what makes it, what makes the sequence sort of countable or easier to count is that it's what we call an arithmetic sequence. So an arithmetic sequence is when each of the numbers in the sequence, there's a constant difference between them. So basically here, there's a difference of 4. There's a difference of 4. Oops. Let's try this. There's a difference of 4 from 9 to 13, and 4 between 13 to 17, 4 from 17 to 21, etc. So that makes it basically arithmetic. And then because we know that this property, we can count it in kind of an easier way. All right.
I have a suggestion.
Yeah.
Why didn't you rather subtract the 9 from the 909 to get 900? Then you divide by 4 to get 225. And since with this you took 9 as 0, you add 1 to it to get 226. And you have your answer.
Yeah, that's completely right. So that's sort of the maybe faster way that we'll get to. So let's move on to some some more examples, and then we'll kind of generalize this pattern. So here I've pulled a couple examples here just to make sure we all get the concept. So for the first one, hopefully it's pretty straightforward. How many numbers are in this list 1 to 100? And feel free to just shout out the answer, but justify a little bit why that's the answer.
I'd say there are 100 terms because you go from 100, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 100. And since you start at 1 and there's a difference of 1 between each term, you know that the last one will be the amount of terms. The last term will be the amount of terms in the entire list.
Yep, that's right. So there's 100 here. I'm just going to write it down. It's pretty straightforward. All right, what about the second one, which is a little bit different in that it starts with 5. So how many terms are in the sequence and why?
I'd say that there are 303 numbers in this list.
And can you just quickly explain how you got that?
Using the method I stated, which is faster when I'm doing it in my head. I just subtract the 5 from the 7 to get 102. And since there's a difference of 1 each time the number changes, there's no need to divide or anything. And taking 5 as 0, 6 as 1, you add 1 to your answer to get 103.
Did you do that?
The way I did mine was that I just minus, because what's it called? The first number is 5. To make it 1, I just minus 5 by 4 and did the same to all the rest of the numbers. And the last number, when you minus it by 4, it'll be 103.
Cool. Yeah, that's another way to do it too. So the technique we did before was let's subtract 4 from each of them. We can get 1, 2, 3, and this gives us 103. Yeah, so this is actually 2 ways of kind of doing the same thing, and it's kind of essentially the same thing, right? So in order to figure out how much to subtract, we kind of look at the first number and we say, okay, it starts at 5. But since we want to map it out to 1, let's actually do it this way. Since we want to map it out to 1, we want to subtract basically 5 minus 1 from it. So basically 107. And then we subtract basically 5 minus 1, which is 4. So this is sort of doing the same thing here. We subtracted 4, and then we got 1 through, and then this minus 4 is 103. So yeah, this is one way where we kind of generalize the formula. And so when we know that formula, we can also calculate things that are a little bit more complicated without having to subtract sort of big numbers all the time. So let's kind of try one more example, which is how many integers are there between 51 and 1007 inclusive? And I want to use this example also because oftentimes in problems, you'll see some of these keywords like inclusive. And so inclusive means you want to include both ends of the sequence. So in this case, you want to include 51 and include 1007. Another term that you might see sometimes is called exclusive, which means kind of the opposite. So if you see 51 and 1007 exclusive, means everything in between there, but not including those two endpoints. So if you see exclusive, it's going to be 52, 53, all the way up to 1006. And when you see inclusive, it's 51, 52, 53, all the way to 1007.
If we see neither, which one do we assume?
Usually people mean inclusive.
Okay.
Yeah. But I would say most of the problems that I see, they'll usually specify, and it's more uncommon to see exclusive, so I would assume that it's inclusive.
Okay.
Good question. All right, so now that we've talked about a couple ways to do this and sort of motivated why this type of formula works, let's try this problem. So someone want to explain what we learned, how it applies to this one?
Well, can I give it a try?
Yeah.
So what I did to solve this question was I found the difference between 51 and 1007, and that came out as 1956. And if you were to individually count each number, you would say 1 on 52. So I added 1 so that which would add the 51. So that my answer became 1957.
Sorry, 1957 or 957?
Sorry, 957. Yeah.
Perfect. Cool. Cool. So here. So you first subtracted and then you said you added 1. So that gives us 957. Yep. And then kind of last question in this series, let's talk about the general formula. So here,
wait,
suppose we have two positive integers. Oh yeah, go ahead.
All right, for the previous problem, didn't you say that inclusive counts with like when you're counting both ends?
Yes.
So wouldn't you add 2 for 51 and 1007?
Okay, so let's look at this. So if we want to include 51, 52 to 1007, we want to include all of these numbers. So kind of using the technique we did before, let's try subtracting 50 from all of them. That gives us 1, 2, 3. And then over here, that gives us 1007 minus 50, which is 957. So you can see there's sort of a one-to-one mapping from this sequence, which is inclusive, to this sequence, which is also inclusive, 1 through 957 inclusive. And so if you count 1 through 957 inclusive, then it gives you 957. total numbers in that sequence. And so the reason you add +1 is when you subtract, one way I think about it is you can have basically the numbers like 1, 2, 3 to 107, and somewhere here you have 51. So if you take 1007 and then you subtract out 51, that actually kind of doesn't count this one. It just gives you how many numbers are on this side. And so if you add 1, then it sort of includes the bottom half, or the bottom starting number. That's how I think about it.
Yeah, I think I got it. Yeah,
Cool.
thanks.
Of course. All right, so now we're going to talk about kind of a formula for this case, which is suppose m and n are positive integers, and m is less than n. So then we have the sequence from m to n inclusive. How many terms are there? So how might you think about this one?
Can I try this one as well?
Yeah.
Okay, so it's in this sequence, each of the values increases by 1 onto the next term. And so if we wanted to make it so that we were having a simple list that was 1, 2, 3, and so on and so forth, you would subtract m minus 1 from each of the terms. And that would give you your final term would be n minus bracket m minus 1, which is the same thing as saying n minus m plus 1. And so there would be n minus m plus 1 positive integers, numbers of terms.
Yep, that's exactly right. So applying kind of what the techniques we were doing before, now we just have n and m as arbitrary numbers. Basically, we take the top number n, and then we subtract out sort of m minus 1 of these, and then we just get n minus m plus 1. So if we think about this, that's sort of how we solved this one, right? So we took 1007 minus 51 plus 1. Or here we took 107 minus 5 plus 1. Are there any questions before we move on to something a little bit more complicated? We'll kind of build on this idea. All right. So now we'll get to another part of that first example, and we'll kind of think about how to generalize this. So now we're going to look at lists that the terms are not 1 apart. They might be 2 or 3 or 5 or 6 apart. And I mentioned earlier, these are arithmetic sequences. So let's look at some of these kind of easy examples to start with, and then we'll generalize from there. So does anyone want to take a stab at the first one, which is how
Could
many
I try?
numbers are on the list?
Can I be sorry? The answer is 100.
Okay, can you explain a little bit why?
Because the difference between each number is +2, and the last term is 200. So I divided 200 by 2, and I divided each number by 2 to make it like the normal counting sequence of 1, 2, 3, 4. I don't know how to explain it well. But the answer is 100.
Yeah, basically that's right. So if you divide, you notice that there's kind of a difference of 2 in each number. So if you divide each number by 2, then you get the sequence 1 to 100, and so there's 100 numbers. That's correct.
Could I try the second one?
Yeah.
I would subtract 5 from 302. And the number you get, you divide it by 3, then add 3.
So you said you would subtract 5 from each one, and that gives us,
basically.
so that would give us 0, 6, right? And then 297. And then, sorry, you then would, did you say divide by 3?
Sorry, I said I subtract 5 from 302.
Oh, okay. Let's try that. Okay, so you want to do 302 minus 5. And that gives us 297.
Then you divide by 3.
Okay. And then what does that give you? Gives us 99.
Miss Wendy, I think it's a simpler way.
Okay, sorry, whoever was speaking earlier, is that the last step or was there?
No, sorry. Then you add 3 to it.
You do add 3 to 99, is that what you're saying?
Yes.
Why is that?
Because you took 5 as 0. So
I kind of have like
Okay.
a different.
So the proposal is maybe add 3 to this.
That's right.
Someone, they had a different idea.
Yes,
wanna try
I
it
have
again?
a different idea.
Someone
My
proposed a different
Yes,
idea.
minus.
yeah, I have a different idea.
What I did was I subtracted 2 from each number to make, cause of the difference between each number is plus 3. So I subtracted 2 from each number to make it all multiples of 3. And then when I did that, I divided the 302. 302 becomes 300. So that I divided that by 3 and divided all the numbers by 3. And then I got 100 terms in the sequence.
Okay, so that's another way you can do it. So basically, the proposal was subtract 2 from everything. So we get the sequence 3, 6, 9 to 300. And then you divide by 3, you get 1, 2, 3 to 100. And that leads us to say there's 100 items in the list.
Yeah. And when I did when I tried the guy that was speaking, I don't know his name, so excuse me to say, but the guy that was speaking before me, I tried his method and his answer was wrong.
Yeah, so let's go back to what this method was saying, right? So it was very close actually. So we took 302 minus 5, that gives us 297. Then we divided by 3, that gives us 99. And then at the end, the proposal was to add 3. That actually, instead of adding 3, what we want to do.
I have a method. I have a method.
Okay, let me finish explaining this one, and then we'll go through if there's another way to do it. So this was very close. Instead of adding 3, we actually just want to add 1. And so if we think about what this is doing, right, it's kind of the same thing. So we take the reason we minus 5, then we'll get, I'll just do it here, 0. If we subtract 5 from everything, we get 0, 3, 6 to 297, right? And then if we divide by 3, then we get 0, 1, 2, and this gives us 99. And so let's say we add 1 to everything, then we get 1, 2, 3, 100. So instead of adding 3, we want to plus 1. And then who's speaking? Was it Keshav? Do you have one more way to solve this one?
Yes, please. I realized that when you divide each of them by 3, you get a remainder of 2. So when you minus 2 and you divide by 3, you get it. So 302 minus 2 is 300. You divide it by 3, you get 100.
Yeah. Yeah. So that's sort of kind of, it's counting in the same way. So basically we want to subtract and we want to divide. And so let's try to distill this down into a more structured way. And we could look at both of these for examples. So let's try a different color. Let's mute. Okay, cool. So for both of these, we want to take, let's think about the sequence. We'll just generalize this. So let's start with M, and let's call the difference like D. So if you have the sequence M, M plus D, M plus 2D, and then we'll call it maybe m plus. Do y'all understand this notation? So basically we have some sequence that starts at m, and then at every step we add a fixed number to it. So if we look at the example here, we have basically 2, 2 plus 2, 2 plus 2 times 2, 2 plus 3 times 2, etc. And then for here we have 5, 5 plus 3, 5 plus sort of 3 times 3 plus 3, which is 2 times 3, 5 plus 3 plus 3 plus 3, basically add 3 to each one. So if we have this sequence, how do we count how many terms here? Well, here we already have basically sort of zero, we can basically say, okay, well, there's sort of 0 plus 0 times d here. So then you can map this to 0, 1, 2, k, which means we have k plus 1 items in here. And so one way to kind of get this when we see these terms without knowing what k is we take this top number, m plus k times d, and then we subtract out our first number, which is m, and this gives us just k times d. Then if we divide by d, which is the difference between the two, then we get divided by, or let's do this. Then we can just divide by, that gives us k. And then we want to add 1 to kind of recap what we were doing earlier here. This is how we get the final number of terms in the sequence. So let's think about applying this formula to here. So for this number, 2, 4, 6, 8, 10 to 200, we could take 200 minus 2. That gives us 198. Then we know the difference between each term is 2, so we can divide that by 2, and then we can add 1. So this gives us 100, which was our answer. And similarly, we did this exact thing here and here, but let's just try to see if this formula works. So we take 302, we minus 5, which is what happened here. We know the difference between each of these is 3. So we divide by 3, and then we plus 1 to account for the first number in the sequence. And this gives us 100 as well. So anyone have any questions about this? It's all counting in different ways, but all right. So let's try one more question that is related. So how many multiples of 4 are there between 202 and 556 inclusive? So can anyone think about how we might map what we just learned to solve this problem?
I think what we could do is we could find what is the closest multiple of 4 to 202
Okay.
after 202, and then what's the closest multiple of 4 before 556, and then we could find the distance between the two factors.
Yeah, that's right. So let's try that. So what's the next multiple after 202?
204.
Right, so 204. And then basically want to keep counting these multiples.
That's a lot.
And then what's the last one?
552.
Go ahead.
I think that since it said inclusive, 556 would be the last one we'd use.
Yeah, that's right. So 552 is the last one that's less than 556, but here, since we said inclusive, we want to include 556. So we want to go all the way up to 556.
Miss Wendy, please, I forgot what you said about inclusive and exclusive. I didn't get it down, so please can you repeat it so I can write it down?
Yeah, of course. So inclusive means we want to include both endpoints. So for example, if we say how many numbers are there between 1 to 100 inclusive, that means how many numbers are in 1, 2, 3, all the way up to 100. If we say exclusive, it means we don't want to include the endpoint. So if I say how many numbers are between 1 and 100 exclusive, then we actually mean the sequence 2, 3, 4, all the way up to 99.
Okay, thank you.
Yep. Cool. So we've turned this word problem into basically how many numbers are there in this sequence. And then now we can apply the techniques that we learned above to count how many numbers there are here. And so basically we can take 556 and subtract 204. And then since we're talking about multiples of 4, there's like a difference of 4 between each number. So we can divide by 4. And then since we want to include 204 in the count, we add 1. So does anyone want to tell me what this gives us?
$89.
Yep. So this gives us basically 556 minus 204 is 352. Divided by 4 plus 1. And then this gives us basically 88 plus 1, 89.
Yeah.
And then one more that's a little trickier. How many perfect squares are there between 97 and 5,000 inclusive? And sort of a refresher for people who know or people who've never seen this, a perfect square is a number that is the result of an integer times itself. So the perfect squares, first couple perfect squares are 1 squared, which is 1 times 1, which is 1. 2 squared is 2 times 2, which is 4. 3 squared is 3 times 3, which is 9. And so on. So these are what we call perfect squares. So any ideas on how we could approach this problem?
I think we'd go about the same way we did the last one, where we find the closest perfect square, the 97 after it, and the closest perfect square before 5,000.
Yep. So the closest one after 97 is 100, which is 10 squared. And then what's the closest one after 5,000?
It's 5,041. That's
So-
71 squared.
So I think it's
Okay.
70 squared because
70 squared is 4,900.
yeah, so
Right.
I have to find the square before 5,000 because we're looking at between 97 and 5,000, so we can't go beyond it.
Okay, yeah, sure. Thank you.
Right, so it goes to 4, which is 70 squared. And so how do we count how many numbers are in this sequence? So this is not an arithmetic sequence, but it is a sequence of squares of sort of an arithmetic sequence. So this is actually 10 squared, 11 squared, 12 squared, all the way up to 70 squared.
I think that we would do this as we did one of the previous ones, where we make it a simple list. So we make it 10, 11, 12. We remove the squares, and then 70 minus 10 would be 60. Add 1, 61.
Yep, that's right. So we notice that this kind of maps to a simpler list, which is 10, 11, 12 to 70. And then we can apply what we learned before. And this gives us 61, that's right. Cool. Are there any questions? We're going to move on to a different topic, more on counting a little bit differently. So this was focusing on lists, and we're going to move on to a different topic unless anyone has any questions about what we just covered here. All right, so I'm going to go back to these notes here. And so here's some more exercises, basically. I'm not going to go through all of these, but these are in the handout. And so when you have time, like you could go through them as homework. The handouts include both exercises and solutions, so you can kind of self-check your solutions. And then if you have any questions about any of them, as I mentioned, you can post or come to office hours about any of the questions on the homework. So we're going to move on to permutations. And I think before we get directly into permutations, let's cover a couple ideas, which is I'll just explain them in abstract, but then we'll do a couple of very simple problems to just understand what they are. So there's two principles when it comes to counting that are kind of what I would call like kind of basic principles of counting. So the first one is often called the addition principle or the rule of sum. And basically in abstract, it says if there's A number of ways to do something, let's call it thing A, and then B number of ways to do another thing B, where A and B are distinct and mutually exclusive. So you can't do both at once. You can do A or B. And the number of ways you can do A or B is just the sum of them. And then the multiplication principle is saying if there's A ways to do something and B ways to do another thing, and those things are independent, so you could do A and then B, or you basically do them together, then the number of ways you can do it together is the product of them. So it's A times B. So that's a little bit abstract. Let's go through a couple simple problems to illustrate the point. So the first question is basically, say Alice is ordering a drink. There's 4 sodas on the menu and 3 juices on the menu. So how many different drinks could Alice order?
7.
Sorry?
7.
Right. So this is just an example of the addition principle. And this is used in kind of, hopefully it becomes intuitive, or it is intuitive, but here there's 4 and 3, and in this case we want to just add them to get 7 because Alice could either get a soda or a juice, not both, so we just add them. Here is another example. So Bob is making a sandwich. He has 2 choices of bread. Say he can choose white bread or wheat bread, and then he has 3 choices of meat. Maybe he can get chicken, turkey, or ham. So how many different sandwiches or types of sandwiches could he make?
6.
6.
Yep. So here we don't add them. We actually want to multiply them because he can pick bread and then a meat. So that gives us 6. Cool. Let's try a different one. So I flip a coin 5 times, record whether it comes up heads or tails each time. So say I flip, it comes up heads, then it comes up heads, then it comes up tails, heads, tails, or something like that. Right? How many different sequences are possible? How would you do this one?
You would multiply the
You multiply
you
number of
multiply
sides
the
by
number of
number of times.
times by the number of choices, whether heads or tails. So it gives you 5 times 2, which is 10.
Okay, so 5 times 2 is one idea. Anyone have any other ideas?
Well, I was thinking you could do 5 factorial. There are 5 factorial ways that it could come up. So you do 5 times 4 times 3 times 2 times 1, and that would give you
120.
So 120 different.
Okay, so here's a couple of guesses. Let's try a simpler question, right? So instead of flipping a coin 5 times, what if this said, let's flip a coin, let's say 3 times, and how many ways are there to do it? And so we could try something simple, like just trying to list out all of the possibilities. So we could do something like heads, heads, heads. I'll try to write a bit. It could come up heads, heads, tails. It could come up heads, tails, heads, heads, tails, tails. tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Did I miss any?
No, I think you got them all.
All right, so how many is that? That's 8. Maybe you try something simpler, see if we see a pattern. If there's one coin, it can come up heads or tails. So that gives us 2. If there's 2 coins, it could come up heads, 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 tails, tails, heads, or tails, tails. That's 4. Does anyone see a pattern?
Oh, 2, 4, 6, 8.
Close. So there's actually not a 6.
It adds by 2. The coefficient increases by 2 every
Perfect square.
time.
Yeah, so basically we multiply by 2 every time. And so one way I think about this is the first time you flip a coin, you can do heads or tails. And then the second time you basically can get heads or tails again. So this is 2, and then you times 2 again to get basically 4. And this is, so let's just go from 2 to 4. This is basically this like multiplication principle in action. So if there's 2 ways to get the first, if there's 2 ways to get the first outcome, which is heads or tails, and then the second flip is also independent of the first flip, there's 2 ways to get that, then there's actually 2 times 2 ways to get 2 coin flips, right? So that's here, heads, 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 tails, tails, heads, tails, tails. And then we can keep applying this multiplication principle. So if there's 4 ways to get 2 coins, and then 1 way to get the third coin, then we do 4 times 2, or 2 times 2 times 2 to get 8. And so if we flip a coin, let's go back to the original problem, 5 times, then we kind of can generalize this and say, well, for the first coin, there's 2 outcomes. For the second coin, there's also, or the second flip, there's also 2 outcomes. For the third one, there's 2. For the fourth one, there's 2. And for the fifth one, there's 2. And so this is actually 2 to the exponent raised to the 5th power. And then, does everyone know what this is?
32.
Yeah, 32. So these were good ideas, but ultimately for this, we actually just want to apply the multiplication principle. And when we think about the multiplication principle, we have to think about it's not how many times by how many, but it's actually for each time, how many outcomes are there. And so here we actually have 5 events, and for each event, there's 2 outcomes. That's why I get 32. And so let's think about something else. Let me see if I have another problem here. Okay. So let's say I have a roll of dice, and the dice has 6 sides. Say I flip the die or roll the dice 3 times and record the number that comes up, 1 through 6. So how many different sequences of numbers can come up, kind of using the same principle? Anyone have any ideas?
Could you please repeat the question?
Yeah, so say I'm rolling a 6-sided die. So the die has 6 numbers on it, and I roll it 3 times. How many different sequences of numbers can come up?
Excuse me, can I answer?
Yes.
So the formula I have generated is the number of choices raised to the power, the number of times is done.
Yeah, so in this case, what would that be? For there's a 6-sided die, and we do it 3 times.
I'm not sure.
6
I'm not sure, but
so
Yeah.
216.
Yeah, so that would be 6 cubed. Does someone have a question on that?
Is that 228?
Let me do it. It's 216.
Oh,
So that would be 6 times 6 times 6.
yeah, sorry, wrong calculation.
All right, let's try one more question too. So this one, it's similar principle, but we're counting something different. So this question is, how many odd numbers with third digit 5 are there between 20,000 and 69999 inclusive? So does anyone have any ideas on how to do this one?
I think we'd have to find some mathematical way to denote which numbers would have a third digit as 5. I don't know how.
Okay.
So
So let me
that's
just write this out. So between 20,000 and 69999, that means that the number has to have 5 digits, right? So let
yeah.
me just write like kind of one blank for each digit.
I think I have the answer.
Okay.
It's I'm not too sure, but is it 2,500?
Can you explain how you got that?
Okay, I'm not too sure about it. And what I did was that it says how many odd numbers is the third digit. Okay. So then the third digit. Oh, okay. I thought it said last digit. Oh, okay. I didn't read the question well.
Oh, that's okay. I think you're close. So let me give a couple hints. So, okay, we have 5 digits. We can think about how many choices there are for each digit. So for the third digit here, it says the third digit has to be 5. So it's basically fixed. Now, if we look at the first digit, what are some options that could be in the first digit? It has to be between 20,000 and 69999.
It can be 2, 3, 4, 5, 6.
Yep. So it could be 2, 3, 4, 5, or 6 here. So let's just write this down. There's 5 choices for the first digit. And all of them are valid because it goes from 20,000. So there's no number here that starts with 2 that isn't valid. And then it goes all the way to 69999. So there's no number that starts with 6 that isn't valid. So any of those could be the next choice. What about for the second digit? Are there any restrictions on that?
1 through 9.
I don't know if it was me. Can you repeat that? All right. So for the second digit, it could be 0 through.
All the way to
Yeah. So it's it can be any digit 0 through 9. So it could be 0, 1, all the way through 9. So there's actually 10 choices here. I won't write this right now. So there's 10 choices for the second one. For the third one, it's actually fixed. So it has to be 5. So there's only one choice. For the fourth digit, it's actually similar to the second digit. There's no restriction. It could be 0 through 9. So there's 10 choices here. And then what about for the last digit?
There are only 5 choices because it has to be odd.
Right. So it says this is odd numbers. So the 5 choices are 1, 3, 5, 7, 9. So there's 5 choices. And as I mentioned, another part of the problem that's really important as we apply the multiplication principle here is that it's between 20,000 and 69999 inclusive. So if this question actually went to like, you know, something in between like 6, 7, 7, 7, 7, then we couldn't just multiply because some of the numbers we're counting would not be included here. But since it's 69999, now we've decided how many choices we have for each digit. And so to count the total number of odd numbers, we actually can multiply them because each digit we can choose independently. And then this gives us 2,500. So whoever said 2,500 before, I think you were really close. I don't know if you did it this way, but this is how we get 2,500.
Yeah, I have a different. I used a different method to do this.
Yeah, do you want to explain yours?
Sure. So, whenever the third digit would have to be 5, that means that there would like the hundreds place would have 5, so it'd be 500, and that happens. And if you count how many 500s there are from 200, and so then from 500 to 599, there's 100 numbers. So then you do that 5 times because you have 20,500, 21,500. Wait, no, never mind. Yeah, wait, no. I think I made a mistake.
Okay. I mean, there are other ways you could do this problem, but I think this one is sort of the fastest way to do it. You can also count how many numbers have a 5 in the middle and then how many of them are odd. But I think compared to this, it may be a little bit harder to make sure you got all of them and you're not overcounting. I think this one's a very fast way to get the answer, but there's other ways too. All right. Does anyone have any questions about this? It's important that we understand the multiplication principle because a lot of what we'll do in the future will build on top of this. All right. Let's try something different. So does everyone know what a divisor is?
Yes.
All right, cool. So just to refresh, just in case, a divisor of a number is sort of a positive integer where if you divide into that number, you get a remainder of 0. So it's like a factor. So let's try this question, which is how many divisors does 12 have? And let's start just doing the brute force way, which is let's just try listing out all the divisors. Anyone want to try that?
Sure. So should I just list them out?
Yeah.
So 1, 12, 2, 6, 3, and 4.
1, 12, 2, 6, 3, 4. Awesome. So we see there's 6 divisors. But let's think about how we could potentially generalize this or do this a different way. If we look at the prime factorization of 12, and I think you guys all learned about prime factorization yesterday, right? Someone want to tell me what the prime factorization of 12 is?
2 times 2 times 3.
2 squared times 3.
2 squared.
Right. Awesome. All 3 of you are right. So it's 2 times 2 times 3, also 2 squared times 3. So then if we think about what makes up a divisor, it has to be something that multiplies into 12. So it has to be some combination of 2s and 3s to make up each divisor. So we could actually write down each of these divisors as some combination of this. So let me just write this out again. So listing out the divisors, we have 1, 2, 3, 4, 6, 12. So 1 is actually 2 to the 0 times 3 to the 0. 2 is 2 to the 1 times 3 to the 0. 3 is 2 to the 0 times 3 to the 1. 4, I'm running out of room, is 2 squared times 3 to the 0. 6 is 2 to the 1 times 3 to the 1. And 12 is 2 squared times 3. So here we can see we actually have all the different sort of possibilities of 2 to the something, where something is less than or equal to 2, and 3 to the something, where 3 is less than or equal to 1. So if we think about possible divisors of 2, we actually see that something is a divisor of 2 if it can be written in the form of 2 to the, say, can be 0, 1, or 2. times 3 to the 0 or 1. So if we think about it this way, we can actually count the number of divisors of 12 using the multiplication rule. So basically, we can first kind of pick how many exponents there are for, or how many powers of 2 there are in the divisor. And so we have 3 choices for that. And then we could pick a choice for the exponent of 3, and we have 2 choices for that. So that gives us 6. Does anyone have any questions or about this reasoning of another way that we could get 6?
So you're looking at the exponents of the numbers that we found can give us 12, and then trying to find out how many of them there are, and then multiplying.
Yeah. So we'll try a more general one right here. So basically, instead of 12, let's say I have a general positive integer n, and we have a prime factorization n, and then we can represent the prime factorization with p1 to the e1, p2, e2, all the way to pk, ek. So p1 through pk are the primes. So for example, with 12, we have 12 equals 2 squared times 3 to the 1. And so we just have a general number n, and prime factorization again shows up in a lot of places. So now we want to count how many divisors does n have. So does anyone want to take a stab at generalizing what we did above? In the case of 12, what we did, right, is we took basically this and this, and we added 1. And the reason we added 1 is because the exponent could be 0, 1, or 2. And here the exponent could be 0 or 1. So there's actually 3 choices here and 2 choices here. And then multiplied it to get 6. So how can we generalize this to a different number n?
We could say something like, for P1, there are P1 to the power of K, because K would be the different possible integers, exponents you can have for P1, and then P2, you do the same thing, you find the possible. So, and then all the way until you reach K, and it'll be P times P to the power of K, which would be all the possible exponents you can have for the final P.
Yeah, I think that's the right idea. So basically, let's look at like a divisor of n. So a divisor of n has to have the form p1 to some number, and that number has to be 0, 1, all the way up to e1 times p2 to some exponent, and that exponent has to be 0, 1, all the way up to e2. It can't be greater than e2. And then all the way to pk, where the exponent of pk has to be 0, 1 through ek. So then if we look at how many choices there are for each exponent, here we have basically there's e1 plus 1 choices for the exponent of p1. There's e2 plus 1 choices for the exponent of p2. And here there's ek plus 1 choices for the exponent of e3. So here we're applying the multiplication rule to basically say, well, to choose the factor of p1 that goes in the divisor, there's e1 plus 1 choices. And to choose the exponent for p2 in the divisor, there's e2 plus 1 choices, all the way up to ek plus 1. And so when we multiply them, we'll get all the possible divisors. And so it's a little abstract, but I picked one more problem that is taking this as another example. So 480, this one's a bigger number. It's a little bit harder to list out all the divisors. Let's start with the prime factorization. So can anyone help me prime factorize 480?
Two to the power of 5 times 3 to the power of 1 times 5 to the power of 1.
Yeah, that's right. And just to kind of show my work here, and this is how you all do it. But one easy way to come up with the prime factorization is basically you can divide. So 480, I'll just divide. I can divide by 4 and divide 480 by 4 gives me 120. Cool. So I was just gonna explain quickly how I prime factorize. So I'll pick a factor of 480 and get 4 and 120, and I keep doing that. So 4 I can write as 2 times 2. 120 I can say 4 times 30. That gives me 2 and 2 again. 30 maybe I can write as 3 and 10. 10 I can write as 2 and 5. And so we can count that up. There's 5 2s. So write 2 to the 5. There's 1 3 and there's 1 5. Cool. So just to be clear, this is 2 to the 5 times 3 to the 1 times 5 to the 1. So how can we count how many divisors 480 has?
Wouldn't we do the previous method of counting the exponent, like plus 1? So it would be 5 plus 1 for 2.
Mm-hmm.
And then 1 plus 1 for 3, and then 1 plus 1 for 5. And then we'd multiply that.
Yeah. Yep. So it gives us 24. And if you were to list out all the divisors of 480, you would also get 24. And I won't do that in class, but if you want to check, you can do this as an exercise. You can list out all the divisors of 480 and kind of match that to all of these possibilities that we've counted out.
Then you can permute the girls before the boys.
Can you explain what you mean by that?
So if there are 9 seats and there are 5 girls and 4 boys, the only way they could sit such that no 2 girls sit side by side is if they sit in a boy girl way, starting with a girl and ending with a girl.
Mm-hmm. So it has to be girl, boy, girl, boy, girl, boy, girl, boy, girl. And that's the only way, yes?
Yes.
So then how many ways are there? Can we arrange these girls and boys to sit like this?
The first girl to be 5, then the next to be 4, then 3, then 2, then 1. Then with the boys to be 4 times 3 times 2 times 1. So it's basically 5 factorial times 4 factorial.
Right. Yep. So just to recap, so there's only one way in which girls and boys generally can be distributed among these 9 seats. It has to be alternating. And then within the girls and within the boys, there's 5 factorial ways to permute the girls and 4 factorial ways to permute the boys. And so that's our answer. And we could multiply this out. It's going to be something like 120 times 24, which is 2880. And then we'll try a couple more. This one, let's use permutation notation again to write the number of ways in which 1 gold, 1 silver, and 1 bronze medal can be awarded to the 48 runners in a race. So how many ways are there to award the medals? And you don't have to multiply it out, just
Well,
how
I
would
think
you express it?
you would do it as 48 permutates 3, since there are 3 different options and to choose from 48 runners. And then, so it would be 48 factorial over 48 minus 3 factorial, which is basically 45 factorial. And then it becomes 48 times 46 times 40, 48 times 47 times 46. Yes, yeah, that's it.
Yep, that's right. So basically we're permuting 3 sort of runners in the race for the first 3. And we can note it as kind of P48.3 or this way. But ultimately what that is we just multiply 48 times 47 times 46. Cool.
I'm
All
sorry,
right.
but could you stay on that screen for just 2 minutes? I just want to write something down.
Yeah, of course.
Thank you.
All right. I'll also share this afterwards. Cool. So here, basically is another example, and we're going to talk a little bit about the difference between replacement, when things are replaced and when things are discarded. So here it's the scenario is my city is running a lottery. In the lottery, there's 25 balls and they're labeled 1 through 25, and they're placed in a bin. And we want to draw out 4 balls one at a time, and their numbers are recorded. And the winning combination is the 4 selected numbers in the order that they're selected. And so how many winning combinations are there if each ball is discarded after it's removed? And then the second case is each ball is replaced in the bin after it's removed and before the next ball is drawn. So let's first focus on the first case. So I draw a ball, and then after I draw each ball, I discard it, I remove it. And then I draw another ball, and I do that 4 times. How many potential combinations are there? Or how many potential winning sort of orders are there?
Well, if you're removing a ball after each time you take it out, that means that the number of balls left will also decrease. So you would start out with 25, then it will be times 24, times 23, and then times 22. And then after that you would stop because you would have found the combination needed already.
Right. So this is in permutation notation. This would be P25 4. And then what about the second case? What if I draw a ball and then I put it back in the bin and then I draw another ball? How would that be different?
It'd be different in the
So I
sense
think
it would be different in the sense that the number would never reduce because you always replace it. So you would always have 25 options. So it would be 25 to the power of 4, since you're only looking for 4 numbers. So 25 times 25 times 25.
Yeah, sorry, did you say 25 to the power of 4?
Yes, please.
Yeah, that's correct. So, and compared to the previous case where we removed the ball, basically the reason it's that is the first ball, it's the same, we can choose 25, but in the first case we removed that ball, so there's only 24 left that we could choose. In the second case, we're putting it back, so there's again 25 that we can pick, 25 that we can pick, and then 25 that we can pick. So that's 25 to the power of 4. So here, just when you're reading through questions or just thinking through it, like be attentive of the nuances between them if something is replaced or if something is really a permutation. So in the first case, it really is a permutation because we are permuting the numbers in the set and we're only using each thing once. In the second case, it's not a permutation, it's just counting the kind of by multiplying. And because we can replace it, each number could be used multiple times. All right. So now we're going to cover a couple of like counting techniques. We'll start with casework. And we have, okay, so again, I have some more exercises here. And we talk about permutation notation. And there's some more exercises. But casework is basically one way that we can start counting more difficult counting problems. And so a lot of these problems that we've solved so far use arithmetic, but some problems cannot just be solved directly using just multiplying things together. And so casework is basically a way to kind of organize your approach to counting, to think about all of the different cases of a problem and then adding up the result from each part. And the adding up the result is sort of that addition principle that we talked about. And so let's look at one example here to get a point across about like how we might do casework. So here, one question is, how many ways can 60 cents in change be made using only quarters, dimes, and pennies? And just to clarify, quarters is 25 cents, dimes is 10 cents, pennies is 1 cent. So how do I make 60 cents using a combination of 25-cent coins, 10-cent coins, and 1-cent coins? And there's a bunch of different ways that you can do this, right? You can start listing out all the different ones like we've done here, but quickly you'll see, oh, wow, there's like a lot of different combinations. And how do we know that we've really identified all of them? So one way to kind of keep your work organized is to divide this into multiple cases. So here we could look at 3 different cases. So basically we could try to come up with 60 cents using 0 quarters, using 1 quarter, or using 2 quarters. And then we know that these are all the cases because if you have 3 quarters, then you already have 75 cents because it's 3 times 25. And that's too many cents. So there's only 3 cases. So if we look at these 3 cases, that actually makes it a lot easier for us to enumerate all the different options so we can count the right answer here. Versus if we don't have these 3 cases and we're just kind of randomly putting down different examples, then it's hard for us to know that we've exhaustively counted something and that we're not double counting. So let's try this out. So in case 1, I said the number of ways would be to say, if we have 0 quarters, how many different ways is there to make 60 cents? And here we can just make a chart to stay organized. If we have 0 quarters to make 60 cents, then we have to use just dimes and pennies to make 60 cents. And so we just have, basically for each number of dimes, there has to be a certain sort of one combination of pennies. So if I use 0 dimes, then I have to use 60 pennies. If I use 0 quarters and 1 dime, then I have to use 50 pennies. If I use 0 quarters and 2 dimes, then I have to use 40 pennies. And we basically have, we can use 0 dimes all the way up to 6 dimes. And we can't use more than 6 dimes either, because then we'll get more than 60 cents. And so here we can see we actually have 7 different cases. So I'll write that right here, 7. In the second case, suppose we use 1 quarter. If we use 1 quarter to try to make 60 cents, then that means with dimes and pennies, we have to make 25 cents. Sorry, yeah, 25 cents. So here it's a bit wrong. Oh, 35 cents, sorry. So 1 quarter is 25 cents. If we want to make 60, we have to do 35 cents. And here, again, we can look at how many dimes we can do here. And so we can have 0 dimes, 1 dime, 2 dimes, or 3 dimes. We can't have 4 dimes because that's too many as well. And so in this case, we have 4 possible combinations. And then finally, suppose we have 2 quarters. If we have 2 quarters, then that's 50 cents. And so we need to make 10 cents out of dimes and pennies. And so there's only 2 options there, which is basically use 0 dimes or use 1 dime. And so I wrote down the numbers here. We had 7 in the first case, 4 in the second case, and 2 in the third case. And so if we want to answer the question overall, we can add up all the different cases, and we get 7 plus 4 plus 2. So there's 13 ways to make 60 cents. And so basically casework is a tool that you can use to help us organize how we count things. Because without breaking it into cases, it would be harder for us to count 13 and in a sort of organized fashion. Does anyone have any questions about this example?
Yes, Ms. Wendy. So I wanted to know, so each case is just giving a different condition that we have to then count in, like the different quarters. So if and you can use the case for any of them. You could have done how many based on dimes and given conditions for the dimes.
Yes, you could have also done it for dimes. The reason that we did it with quarters is that it was actually divided it into fewer cases. If you do dimes, then there could be 0 dimes, 1 dime, 2 dime, all the way up to 6 dimes, and then you have 6 cases. So you could also do it that way, but it would be a little bit harder, I think, to go through all 6 cases.
Okay, thank you.
But you could get the same answer by doing it that way.
Okay, thank you.
Yeah. All right. I'll go through one more example. There's actually 3 examples in this worksheet, but we'll just do one more together. And then you can take time to look at the third one on your own. So here we have 3 people, Alan, Ben, and Carl. They have 8 jelly beans and they all look and taste the same. So how many ways can the 3 boys split up jelly beans so that each of them gets at least 1 jelly bean? And you can't have half jelly beans. That has to be a whole jelly bean. So here we can kind of make this a little bit more mathematical. So let's say, okay, Alan gets A number of jelly beans, Ben gets B jelly beans, and Carl gets C jelly beans. And then we know there's 8 total. So A plus B plus C equals 8. And then we also know that since each of them gets at least 1, then A, B, and C have to be at least 1. So we can organize, again, this into different cases. Here we can look at maybe the value of A as an example. So if Alan gets 1 jelly bean, or if A equals 1, then we see there's actually 6 different options, because Ben could get, B could be 1, 2, 3, 4, 5, or 6. B can't be 7 because we know C has to be at least 1. So here we have 6 options. Similarly, we can say, okay, well, when A is 2, how many options are there? And here B could be 1, 2, 3, 4, or 5. When A is 3, B could be 1, 2, 3, or 4. So that's 4 options. When A is 4, there's 3 options. When A is 5, there's 2 options. And when A is 6, there's just 1 option. And so here we've just basically listed out all the different possibilities of A, B, and C to satisfy the equation A plus B plus C equals 8. And then A, B, and C are all at least 1. So if we add up the result from all the cases, then we basically see that the number is 6 plus 5 plus 4 plus 3 plus 2 plus 1. So that's 21. So there's 21 ways that the boys can split up the jelly beans. So this is kind of an example where you can use algebra to kind of help you with some counting problems. So we'll use algebra more often in some of our future problems, but it basically adds structure to a word problem where it's just like 3 people and jelly beans. You can transform that into an algebra problem with like A plus B plus C equals 8.
Could I ask a question?
Yeah.
Just as you have factorial where it's the number times the number below it continuing. Do you also have a term where it's the number plus the number below it plus the number below it and continuing?
I don't see it as common. I think people usually, there's sort of a summation notation that you sometimes see. So you could say like sum of n equals 1 to 6 of n. This is 1 plus 2 plus 6. But it's not as common to write it out that way unless you have a more complicated formula. Oftentimes you'll just see 1 plus 2 plus 6. But factorial is kind of special because we use it in different ways.
Okay, thank you.
Yeah.
I think that there is a formula when that happens that is pretty useful.
Yeah, there's a formula for calculating it. I guess the question was around notation. But yes, to calculate the formula, I guess this is a little bit more algebra, but basically you can take the first number, the last number, add them together, times the number of terms and divide by 2.
Yeah.
So, yeah. All right, let's do a couple of examples. So this first example, we just went over how to do it. Here's one more example. So we have 3 fair 6-faced dice of different colors are rolled. How many ways can the dice be rolled such that the sum of the numbers rolled is 10? So what cases might we want to use for this one? Anyone have an idea?
Well, since it's a 6-sided dice, our cases would be 1 all the way up to 6 for one of the dice. So you have the first row being 1 all the way up to 6.
Yeah, so this is actually pretty similar to the other question. So they're different colors, so we could denote the first one by A, second one by B, and the third one by C, and we know that the sum is 10. And then we could look at the different values that A could take on. So if A is 1, then let's just write A, B, C. If A is 1, what can B be? So B can actually not, if B is 1, then C has to be 8, and that's not right because dice can only be, so the dice can only be 1 through 6. So the lowest that B could be is actually 3. And when B is 3, C is 6. Does everyone see why that's true?
Yes.
Yeah.
Okay, cool. And then B could also be 4. In that case, C is 5. B could also be 5. In that case, C is 4. And then B could also be 6. In that case, C is 3.
Yeah.
If A is 2, then B could be 2 and C is 6. B could be 3. C is 5. B could be 4. C is 4. B could be 3. B could be 6. Sorry. I meant to write 5. Sorry. B could be 5 and 6. C could be 3 and 2. If A is 3, similarly here, B could be 1. C could be 6. B could be 2. And then B could be all the way up to 6, where C is all the way down to 1. I'm just abbreviating a bit here. Let me know if you want me to expand it. If A is 4, do A, B, and C again. Then B could be 1, and then C would be 5, and B could be all the way up to 5, and then C is 1. But D can't be 6 because then C would have to be 0. Similarly, if A is 5, then B could be 1, then C would be 4. B could be 2, C would be 3, and then B could be 4, and then C would be 1. And finally, if A is 6, then B could be 1 and C is 3, B could be 2, C is 2, or B could be 3, C is 1. So now we've kind of organized all the different cases. Now we can sum up all the numbers to get the total number of ways to do this. So here, if A is 1, we see there's actually 4 ways to do it. If A is 2, there's 5 ways to do it. If A is 3, we have 6. If A is 4, we have 5. If A is 5, we have 4. If A is 6, we have 3.
Miss Wendy,
Yeah.
for the A is 1, can't you have other options like B might also roll 1 and C might roll 5, or B might roll 5, or 1 might roll 2?
Yeah, so here I'm looking at the part of the question that says the sum of the numbers rolled is 10. So we only want to count the cases where A plus B plus C equals 10.
Okay.
So if
sorry.
A rolls 1 and B rolls 1 and C rolls 5, then the sum is 7. If A rolls 1 and B rolls 1, then the only way to get 10 is if C is 8. But with a die, you can only roll 1 through 6.
Okay.
Yeah.
Thank you.
So here, if we sum them all up, we get 4 plus 5 plus 6 plus 5 plus 4 plus 3, which is just all of these numbers here that I'm summing up. And then what does this give us? 27. All right. And then let's do a little bit more of a complicated one, which kind of combines casework with some of the earlier concepts that we talked about with permutations and multiplication. So here we have a fictional island Mumble, and we have this Mumblean alphabet. It only has 5 letters, and every word in this language has no more than 3 letters in it. So how many different words are possible? And a word can basically use a letter more than once, but 0 letters doesn't count as a word. So how would you guys approach this one? Do anyone have any ideas? So let's say the alphabet, let's just make it concrete. Let's say the alphabet has 5 letters and the letters are A, B, C, D, E. And then every word has no more than 3 letters. So, and 0 letters doesn't count. And so basically I could start enumerating example words. So maybe A is a word, A is a word, A, B, C is a word, B, A, C is a word, etc. But that's not very wieldy. We want to maybe divide it into different cases. So what cases could we look at here?
We could look at the 5 different letters, and then we can look at how many can do a word. So the first case would be all containing A, then second case containing B, or rather, sorry, starting with A, starting with B, starting with C, starting with D, and starting with E.
That's one way you could divide it that way. But I think if you did it that way, you might still have other cases to consider. So let me propose another way we could divide it into cases. So one way you could divide into cases, kind of orthogonal to that, would be looking at the length of each word. So here in some examples, some of the words are 1 letter long, some of the words are 2 letters long, and some of the words are 3 letters long. So let's see what happens if we divide it into those 3 cases. So if we have 1 letter words, how many 1 letter words are there?
5.
Yep, there's just 5 because it's just A, B, C, D, or E. What about 2 letter words?
Ten.
How did you get that?
Because we'd be multiplying. Wait, never mind.
And actually, it's 25.
5.
And why is that?
yeah.
Because then each letter would have the next letter. So the possibility for each of them is 5. So it comes 5 times 5. Or
Yep.
5 raised to the power 2.
Yep, that's right. So it's 5 times 5, it's 25. And then finally, the third case would be 3-letter words. How many different 3-letter words are there?
5 raised to the power 3.
Yeah, so same
120.
reasoning. There's 3.
125.
Yep. So there's 5 choices for the first letter, 5 choices for the second, and 5 for the third. So there's 125. And so if we put these 3 cases together, we can actually sum them up and we get 5 plus 25 plus 125. And this gives us 155. All right, we have about 3 minutes left. Let me just do one last problem and then I'll let you all go. So this one is, how many 3-digit numbers have exactly 1 5? So anyone have ideas on how we can split this into
You
cases?
could do it based on the position of the 5. 5 is the first digit, 5 is the second digit, and 3 is, and the last digit is 5.
Yeah, that's right. So we could split it up into the position of the 5, and we'll see why these are different cases too. So let's say the first case is, it starts with 5, and then we have 2 spaces. The second case is the 10th digit is a 5, and the third case is that the 1 digit is a 5. So in the first case, how many 3-digit numbers start with 5 and have exactly 1 5?
Would you think about it as the fact that you can't, you look at the first 9 numbers and then you'd remove 5 from it, so each of them can have, each of the positions can have 8, so it'd be 8 times 8.
That's really close. So there's actually, it's actually
I think
9
it's
times
8.
9.
Yeah, 9 was the 0 part.
Yeah,
so
yeah. So it's 9 times 9. And basically, you have to count 0. So there's 0, 1, 2, 3, 4. And then we skip 5, 6, 7, 8, 9. So that's 9. What about the second case? So this is 81.
Since you can't start with 0, else that will make it a 3-digit number. You have to skip 0 and 5, so you get 8. But the next one, since it's after the 5, you can add 0 to it, so it becomes 8 times 9.
Yep, that's right. And then what about the third case?
You can't start any of them with 0, else that will just make it 5. So you have to skip both 0 and 5 for both of them, making it 8 times 8, which is 64.
That's close. So yes, you can't have 0, 0, 5, but if you already have the restriction on the first place, so this one cannot be 0.
Yeah.
This one could be 0. So this one is 1, 2, 3, 4, 6, 7, 8, 9. This one could be 0, 1, 2, 3, 4, 6, 7, 8, 9. So it's 8 times 9 again, and this is 72. So we could add this up. It's 5,
2 to 5.
carry 1, 15, 20, 235. Did I add that right? Yeah. Cool. Any last questions? I will share these notes into our Piazza as well. And then I'll also, basically you all can refer to these questions plus these notes for some additional practice problems. So here there's more problems, and then they also include some solutions. And then I know there's some other topics here that we didn't get to, such as like overcounting and complementary counting, that we'll cover in the next week.
I think there's 225, not 235.
Yeah, it's 225, not 235. Because it's 2 plus 2 plus 3, so there shouldn't be any 10.
Oh, sorry. Yeah, you're right. 225. Yeah, good catch. All right. Any last questions?